All right, so Unit 3 of trigonometry is about verifying. And verifying is where we want to verify that an identity is true. An identity is basically an equation which sets two expressions equal to each other, and those two expressions don't actually look very much alike to begin with, and our job is to manipulate one side of the equation until it is indeed exactly the same as the other side, and hence we have verified that the equation is actually true. You are going to be playing a little bit of the role of a detective in this unit, because unlike previous units where we were able to give you kind of a step-by-step, here's what you do first, here's what you do second, kind of system to use, verifying is a little trickier, because you can use 10 different tricks on the first step on 10 different problems. It doesn't follow the same order in what you do every single time, and so that can be a little bit difficult to begin with until you practice enough. And once you've practiced enough problems, you start to see tendencies and similarities in new problems that you already have done had, and then you can start using the same tricks. And so you really have to kind of have your eye out for structures of problems. You have to be willing to look for little clues, and that's where the whole detective idea comes in. Here's the general idea once again. We have an equation. We have an equal sign saying that this blue rectangle is equal to this red pentagon. And of course they don't look anything alike, and geometrically they would not be equal, but this is just the idea here saying, hey look, if I tell you these are equal, if I tell you that this identity is true, there should be some way that you could take one side of the equation, for example, the red pentagon, and manipulate it until it becomes the blue rectangle. Of course, we're not dealing with shapes, we're dealing with trigonometric expressions, and you're going to be relying a lot on the identities that we discovered together in Unit 1. In fact, this page, and this is the first page of your course pack, Unit 3, is just guidelines for verifying identities. So they're not like step 1, step 2, step 3, like some of the notes pages that you've seen in the past. It's just some ideas to help you along the way. Number 1, learn, know, live, and breathe your trigonometric identities, particularly the fundamental identities, the reciprocal identities, and the Pythagorean identities. The fundamentals would be like tangent of x is sine x over cosine of x. Reciprocals like secant of x is 1 over cosine of x. And the Pythagorean identities, the main one being sine squared of x plus cosine squared of x is equal to 1. And then the two others that spawn from that. Now, every once in a while you may need to throw an even-odd identity in there or a cofunction identity in there, but the other three are primarily the ones that you're going to be using the most of. Almost always start with the side containing the more complicated expression. It may be a little counterintuitive to say, ooh, this side's uglier, I'm going to start with it, but it's actually much easier to take something kind of big and ugly and simplify it to something smaller than it is to take something kind of small and simple and make it into something more complex. And once you've tried a couple, if you try a couple of these different ways, you'll see that simplifying something big and ugly down is much more intuitive than it is to go in the reverse order. Hint number 3, rewrite sums or differences of quotients as a single quotient. I really just call this put two terms together to make one term. If you look at the other side of an equation and you say, hey, this big ugly thing is pretty ugly, but it's just one single term, whereas on the other side I have two separate terms, then something that would be a good idea is for me to put these two things together, which would require a common denominator. And so you do a little bit of algebra to do, to get a common denominator and then put them together, and sure enough, a lot of times you'll find that your identities fall into each other very quickly. But that's another hint that comes in handy quite often. Number 4, sometimes rewriting one side in terms of sines and cosines only will help, especially where there are long strands of multiplication in the problem. We saw this back in Unit 1. In Unit 1, we saw in the simplifying problems where if we had a bunch of terms, once we got the angles to be equal and we turned everything into sines and cosines, we'd either get sines and cosines canceling each other or turning into sine and cosine squareds, and then we could use Pythagorean identities, and you'll see a lot of that happening again with these identities. Number 5, sometimes multiplying the numerator and the denominator by an appropriate factor, which is usually a conjugate, will result in a simplification. What is a conjugate? Well, here is a really good example of conjugates right here. This guy right here, 1 minus sine of theta, and this guy right here, 1 plus sine of theta, are conjugates of each other. So basically a binomial with the opposite sign in between. So one of them's addition, one of them's subtraction, are conjugates. And the reason conjugates are so powerful is because when you multiply conjugates together, when you FOIL them out, the middle terms always cancel, leaving you with something that we remember fondly from algebra called the difference of perfect squares. And 1 minus sine squared is something that is substitutable from a Pythagorean identity. And if you follow this line across, you will see, there it is right there, cosine squared. If you go to the Pythagorean identity, sine squared theta plus cosine squared theta equals 1, and you manipulate it, you'll find that cosine squared theta is equal to 1 minus sine squared theta. So great trick to use quite often, and we'll be pointing that out when it pops up. Always keep your goal in mind as you manipulate one side of the expression. Keep your eye on the other side of the expression so that you might have clues of what would make sense to do. Like if you look at the other side and it's one term, and yet on the side you're manipulating you have two terms, why don't we try to get those two terms together, usually through getting common denominators. If you look at one side of an expression that's factored and your side is not factored, maybe we should do some factoring, which is something we'll review in a couple days. And finally, warning, do not treat these as though you were solving an equation. And this is one of the biggest pitfalls that some students fall into early on in this unit, is they'll do a little something to one side and then a little something to the other side, and maybe they'll add something to both sides or divide both sides by something. You're not allowed to do that. With an identity, we want to prove that one side is exactly equal to the other side as it began. And so once we start manipulating one side of our equation, we must leave the other side alone all the way through the problem. And if you just follow that rule, it'll save you, a lot of confusion. But you're simply not allowed. It's not that it's algebraically illegal, but for what we're doing, which is verifying identities, we have to leave one side as it was at the very beginning. That's the rule of doing an identity. So now that we've talked through this a little bit, let's go ahead and jump in and do some examples. These are the same examples that are in the packet that was passed out to you. These are the same exact problems from page 190 in your textbook. Problems 1 through, I believe, 17 odd are the ones we're going to go through. And of course, the assignment was then to do the evens, which are very similar to the odd. So if you work your way through the odd problem, you should have a good clue on how to do the even problem. Right away, I see a little multiplication going on here. And so that tells me, hey, maybe I should change everything in the sine and cosine. And so I'll go ahead and turn cosecant into its reciprocal identity, which is 1 over sine. So we end up with something that looks a little bit like that. Multiplying 1 over sine by cosine gives us cosine theta over sine theta, which is a fundamental identity. That is cotangent theta. And we're done. As soon as your original, the side that you're manipulating equals the side that you left original all the way through, you know that you have finished that identity. So this one was pretty short, pretty sweet, not too bad. A couple things to point out along the way. For example, some people ask, hey, if I know that this side's going to be the same all the way down, if I know that this is never going to change, can't I just, just kind of leave that out until the very end? Can't I just kind of leave it and then throw the cotangent in at the end? Or can I just, kind of do the quotation, what do you call those little things? Ditto marks all the way down? No, unfortunately, you can't shortcut your way around these. And that's why we were, pretty strict on the way we graded things to begin with. This stuff has to be in there for it to be fully accurate. It has to be a full equation, every single line. You can't skip steps. You can't do double steps. Every line is either going to be an algebraic manipulation, maybe that's multiplying two things together, like we did in this line right here, or maybe that's factoring something, or maybe that's multiplying something through. But regardless, it's either going to be an algebraic manipulation or it's going to be a trigonometric substitution. And you can't change anything, any one term in two ways or more in one step. So just make sure you're not trying to shortcut, and you'll do fine on this stuff. Let's take a look at the next example. This one is one of the few problems where you might actually have to use an even-odd identity. And what we see, right off the bat is the negative angle. Now remember, when I use, well, first of all, let's remember that tangent is odd. So that means that when I take the tangent of a negative theta and turn it into the tangent of a positive theta, I get the opposite ratio. But also remember order of operations. Remember that before I do anything, before I try to add the negative tangent, I'm always going to do exponents before that. And so it's just a little tricky thing you got to keep in mind. But the truth is that when I square a negative, it's going to turn back into a positive anyway. And so we end up with 1 plus tangent squared positive theta is equal to secant squared. And this is one of our Pythagorean identities. In fact, this is the exact form of one of the three Pythagorean identities. 1 plus tangent squared is equal to secant squared. And so 1 plus tangent squared can be substituted with secant squared theta, and we're off to the races. I know the handwriting on this smartboard is not perfect. Because of the recording thing slows down the processing speed of the computer, it gets a little bit iffy with the writing, so I will apologize for that ahead of time. Here's one thing to keep in mind. Every step is either going to be trigonometric or algebraic. Here is a trigonometric substitution right here. This was an even-odd substitution up from the very first line. But then the very next step is algebraic. When you square a negative, you get a positive. That was algebraic. And then our last step is, once again, trigonometric. 1 plus tangent squared is secant squared. Every move you make with a verification is either going to be algebraic or trigonometric substitution from your identities. So the one thing I will say is just try not to do too much at once. If you have an extra step in it, that's fine, but if you're missing a step, then you start losing points. So just be very conscientious about that. Let's look at our next example. Cosine of theta times the quantity tangent theta plus cotangent theta, and it's supposed to be equal to cosecant of theta. Most of these, it looks like the simpler expression so far has been on the right. That doesn't mean you can't manipulate the right and leave the left alone, but I will tend to do the more complicated side and leave the easier side alone, and so far we're manipulating the left side of these. I think the first thing I'm going to do is I'm going to do a little algebra. I'm going to distribute the cosine through. So cosine theta tangent theta plus cosine theta cotangent theta is equal to cosecant theta. All right. Now that I have a little bit of multiplication here and here, it makes sense probably to turn everything into sine and cosine. So cosine is already cosine. He stays the same. Tangent's going to turn into sine theta over cosine theta. Cosine theta, once again, stays the same. And cotangent theta is going to turn into cosine over sine. And I know, once again, some of this handwriting's awful because for some reason the computer doesn't like it, but hopefully it still helps you out a little bit. All right, so a couple good things happen. One good thing here is that the cosines simply cancel, leaving me with sine theta Over here, the cosines do not cancel, but they go together quite nicely to give me cosecant squared of theta, and that's over sine of theta. So here's where we start looking for patterns. And I look at the right side of this. This is what I'm searching for. This is what I'm trying to get to. And I notice there's only a single term, just one term. Whereas when I look at this other side, I have two terms. I want to put these terms together, but I can't add them together unless I have a common denominator, which is just sine. So I'm going to go ahead and multiply this dude by sine over sine. Once again, showing my work so that we all understand where the new line is coming from, which is going to be sine squared plus cosine squared over sine. Okay, we now have our common denominator, and that's equal to, once again, cosecant theta. Well, this is where our Pythagorean identities come in very, very handy. Sine squared plus cosine squared, right here, cosine squared plus sine squared, is equal to 1. 1. So we're just going to substitute 1 in for sine squared plus cosine squared. But wait a second. What is 1 over sine squared? Well, that's just a reciprocal identity. Reciprocal of 1 over sine squared is cosecant. That's the definition of what cosecant is, the reciprocal of sine. And all right, very nice. We're done with this verification. So this one was a little bit longer. Had to do a little algebra to begin with, then some trig, moving everything into sine and cosine, and then some algebra, got a common denominator, then some trig, Pythagorean identity, and then some trig, reciprocal identity. Every move is either going to be algebraic or trigonometric. This next one is, let's see here, what am I going to do? I guess we could turn everything into sine and cosine just right here with the tangent and cotangent, but it might be easier just to leave the tangent alone. We know that cotangent is the reciprocal of tangent. I could just turn cotangent into 1 over tangent, subtract cosine. You could certainly turn everything into sine and cosine, and you get, sine over cosine times cosine over sine, which would cancel out also, but it's just a little less writing to see that this cancels into a 1. And this pushes us immediately back into the land of Pythagorean identities. The primary identity we're referring to now is sine squared plus cosine squared is equal to 1, which if I subtracted a cosine squared from each side would give me this identity. 1 subtract cosine squared is equal to sine squared, so 1 subtract cosine squared is equal to sine squared. And we are done. We're done. So that one is actually pretty quick. Once I did a little cancellation with the tangent and the cotangent. Our next one is a binomial times a binomial. So we're going to have to do a little FOIL here. And what we're going to do is we're going to multiply secant by secant. That's going to be secant squared. Now remember, these are conjugates of each other. Secant minus 1, secant plus 1, those are conjugates of each other. In more simple algebraic terms, if we had x squared minus 9, like from algebra 1 or algebra 2, and we, not x squared equals 9, but x squared minus 9, and we factored this into difference of squares, x minus 3 times x plus 3, these would be called the conjugate pair. And so anytime that you multiply two conjugates together, you're always going to get difference of squares because the middle terms cancel out. And that's exactly what's going on here. I'm going to get a negative secant and a positive secant, and those just go away for us. And so all we really have left is the negative 1 times 1, which is minus 1. Now, for those who aren't too familiar with identities, that may not really help you much, but for those of you that are familiar with particularly your Pythagorean identities, we're like, hey, wait a second. Tangent squared plus 1 is equal to secant squared, so if I subtracted 1 from each side, secant squared subtract 1 would be equal to tangent squared. And we're done. 2 steps, not too bad. Some of these are fantastically short. That doesn't mean they're easy, because sometimes it takes a minute to see exactly what's happening, but short. Other ones are long. You'll have verifications that may take you 8, maybe even 12 lines sometimes. So there's a balance, but we're certainly starting off with some of the ones that aren't too long. Here's one that's almost exactly the same as the one we just did. Difference of squares. Secant times secant, secant squared. The middle terms, which would be a positive secant tangent and a negative secant tangent, cancel out, leaving us with only a negative tangent squared. And you may be like, hey, wait, isn't negative tangent squared the negative like gets squared into a positive? Well, no, because here I'm multiplying a negative tangent times a positive tangent. And so the tangent times tangent is tangent squared, but the negative times positive is indeed a negative. So don't let that confuse you there. But let's go back to our identity. Tangent squared plus 1 is equal to secant squared. If I subtracted tangent squared from both sides, secant squared subtract tangent squared is 1. 1 is equal to 1. I have verified this identity. I've verified that this original expression is indeed equal to the other side. Okay, that's what verifications are all about. All right, next one. Cosine squared times 1 plus tangent squared, quantity 1 plus tangent squared is equal to 1. So let's go ahead and do a little distribution. I just don't see any multiplication on the other side. I mean, all I see is a 1 over here. So it doesn't really make sense to try to keep separate terms. So let's just go ahead and multiply the cosine squared through the binomial. We're going to get cosine squared plus cosine squared times tangent squared. As soon as I see a couple trig terms being multiplied by each other, like right here, I'm like, yeah, maybe turning everything into sine and cosine would be handy. And so I'm going to do it. I'm going to turn tangent squared into sine squared over cosine squared. And sure enough, the cosine squareds cancel, leaving me with cosine squared plus sine squared is equal to 1. And we know that the very first Pythagorean identity that we ever came up with back in Unit 1 was that sine squared plus cosine squared was equal to 1. So there we go. We are done simply by distributing and then a little algebra and then a Pythagorean identity. All right, this one is a little bit more interesting and much more prone to mistakes. And the main reason it's more prone to mistakes is because people forget to FOIL. A lot of folks are going to just come up and say, hey, you know what? I think that sine squared, or sine plus cosine quantity squared is equal to sine squared plus cosine squared. And no, that's not actually true. Whenever you square a binomial, you have to multiply the binomial times the binomial. And so you're going to have to FOIL it out. You're going to have to do the sine times the sine, which is sine squared. Then you're going to have to do the outers, which would be sine times cosine, which is sine cosine. Pretty exciting there. And then the inners, which is another sine times cosine. So now we're up to 2 sine cosines. And then finally, cosine times cosine, which is cosine squared. Okay. Here's just a real basic algebra 1 or algebra 2 type problem. This is not equal to x squared plus 9, because what it is equal to is x plus 3 times x plus 3. So you have your firsts, which is x squared. You have your outers, which is 3x. You have your inners, which is 3x. And then, of course, the lasts, which is the 9. And so you'd be missing a 6x term if you tried to shortcut this over here. That's why you have to remember to FOIL, or it's really just distribution. FOIL is a way to remember the parts of that distribution, but people seem to remember it. Let's do the second binomial that's being squared, which is very similar to the first. We're still going to get a sine squared, which is good. And we're still going to get a cosine squared at the end, but the middle terms this time are going to be a sine theta times a negative cosine theta, which is actually a negative sine cosine, and then another one of those. And so we're going to get negative 2 sine cosines, and then the cosine squared that we mentioned at the end. and this whole thing's equal to 2. All right. So one good thing that I bet most of you see is that we have a positive 2 sine cosine and a negative 2 sine cosine, and those are just going to kind of go away for us, which is awesome. What do I have left? Well, I have sine squared plus cosine squared plus sine squared plus cosine squared, and that's all equal to 2. I could have kind of combined like terms a little bit and done 2 sine squared plus 2 cosine squared and then factor out a 2. That just would be another way of organizing the algebra. But I think it's easier for you guys to maybe even see it this way. What is sine squared plus cosine squared? Oh, wait, we know that's a Pythagorean identity. That's 1. Hey, wait, look, it's another sine squared plus cosine squared. That's another 1. And now we're back to kindergarten math. People are always like, hey, what's honors trig? Okay, is it like 1 plus 1 equals 2? Hey, every once in a while it is. Every once in a while, 1 plus 1 is equal to 2. And we have verified this identity. All right, here's something we have not done much of yet, and it's factoring. We're going to actually do a lot of factoring in this chapter. But the way we start off is just with some little simple factoring tricks. We're going to do a whole day reviewing factoring techniques coming up here in a couple days. But for now, we'll just do it real simple. Okay? When we look at this and this, these are 2 terms here. What do they have in common? What do they have in common? It's like if I had x to the 4th subtract x squared, what would they have in common? Oh, they have an x squared in common. I could take the x squared out, leaving me with an x squared here, and then x squared divided by x squared is 1. If I redistribute it, I get right back to where I began. And that is some, Algebra 1 factoring called factoring out a common term. That's what we're going to do on this problem right here. We're going to go ahead and factor out the secant squared, leaving me with another secant squared left here, but only 1 left here. Now, this, although it changes the format of the problem, may not seem terribly productive to begin with, but once we have broken these into squares, I can start to say, hey, wait a second. Don't I know an identity that has secant squareds and tangent squareds? Don't I know an identity that's like 1 plus tangent squared is equal to secant squared? Don't I remember that somewhere from earlier on, like in Unit 1? Yeah, we do know this. And so we're going to use that back to back right now. Your secant squared is equal to 1 plus tangent squared straight out. Okay? So 1 plus tangent squared. On the other hand, what does secant squared subtract 1 equal to? Well, I'd have to subtract this 1 on the other side, right? Secant squared minus 1 would be equal to, tangent squared. And so what I've done now, through some substitution of Pythagorean identities, is I have changed all the secants into tangents, which is good, since our right side here has nothing but tangents. I'm going to now redistribute what I have going on here. I'm going to get tangent squared plus tangent to the 4th is equal to tangent to the 4th plus tangent squared. All right? And then finally, I'm going to go ahead and erase this. I think it's served its purpose. If you ever do side work, I really don't mind if you do it. Just make sure it's away from the bulk of the problem. Now we just have to do one step. Most people would be, well, aren't we done? You're adding 2 things that are the same. Aren't they the same? Well, yes, but the rules for verifying are very strict, and they say you have to be identical. And so we are actually going to go all the way to the last step of commuting these 2. It's the commutative property that says, if A plus B is equal to B plus A, and we're going to change the order of these 2 terms so that it does match precisely the other side. I know that seems a little nitpicky, but you're just going to have to trust that I'm not the one that made the rules of verifying up. They've been around for hundreds of years, so just play by the rules, and you guys are going to do really well in this unit. That is the examples that got you up through basically problem number 17 of page 190. The problems that were your assignment over the last couple nights, problems 2 through 18 even on page 190, can be modeled with those. I hope this video helped you out. You'll be seeing some more examples from the packet tomorrow, and then you'll do some more problems from page 190 tomorrow night. And as always, please come in and get help if you're struggling with any of this at all. The only thing you can really do to hurt yourself is to not practice these at all. This is a new kind of mathematical process you just haven't done before in any math class you've ever been in. And so it's very important that you try practicing to try to get this stuff down. Hey, take care. We'll see you soon.